Good afternoon, everyone. For researchers and scholars, today we explore variational autoencoders and the reparameterization trick. We'll unpack what VAEs are in plain terms, why they hold promise for learning compact generative representations, and how the reparameterization trick makes training feasible by moving randomness outside the gradient. We'll also survey real-world applications and what these ideas can do in practice, from unsupervised representation learning to data synthesis and beyond. By the end, you'll have a concrete mental model of how VAEs work and why the reparameterization step matters for scalable inference. Today we'll cover what VAEs are and why they matter, then dive into the latent space, the compact, hidden map they learn. We'll build the probabilistic intuition behind VAEs, the role of randomness and probability in modeling data. Next comes the training objective, the goal we optimize to make good generative models. We'll explain the reparameterization trick, the trick that makes gradient-based training possible. We'll look at the standard VAE architecture and its core building blocks, then discuss where VAEs shine in real-world applications. We'll touch on limitations and challenges, and then explore a few advanced variations that push the method further. Finally, we'll preview future directions researchers are pursuing. Now, we turn to a clever kind of neural network called a variational autoencoder, or VAE, and how it pairs understanding with imagination. Think of an encoder that doesn't hand you a single code, but a probability map, a compact latent space where nearby points look similar. Then, a decoder that can sample from that map and recreate data that feels familiar yet new. This probabilistic stance gives VAEs two big strengths: efficient data generation and meaningful latent representations. Unlike a traditional autoencoder, the VAE learns distributions and uses sampling to produce variety, while balancing reconstruction quality with keeping the latent space well behaved. We'll walk through the three actors: encoder, decoder, and latent space, and how they compress, reconstruct, and generate. Finally, expect concrete examples from art, science, and unsupervised learning, plus what smooth interpolation lets us do. Building on the basic VAE we've discussed, a family of extensions pushes the framework toward more expressive generation, more interpretable latent structure, and sharper samples. Here's how three popular directions unfold in practice: beta VAE, info VAE, and VAE-GAN hybrids, with a note on latent disentanglement. First, beta VAE. The key idea is to modulate the regularization strength that ties the latent posterior to the prior. In the evidence lower bound, we replace the standard KL term with a weighted version: reconstruction loss plus beta times KLQ vertical bar X vertical bar PZ. Increasing beta encourages the model to carve the latent space into simpler, more separable factors, often yielding more disentangled representations, where a single latent dimension tracks a single factor of variation. The trade-off is clear: stronger disentanglement can degrade reconstruction fidelity. In practice, researchers use beta schedules or warm-up strategies, starting with beta near 1 and gradually increasing it, while monitoring both reconstruction quality and disentanglement metrics. Beta values well above 1 frequently yield noticeable disentanglement on benchmark datasets at the cost of some detail in generated samples. This approach is especially appealing when interpretability and controllability of latent factors are primary goals. Second, info VAE. This variant tackles information preservation differently. It seeks to prevent posterior collapse and to ensure that the latent code retains meaningful information about the input. Rather than a pure KL penalty, info VAE adjusts the objective to balance the mutual information between X and Z with a divergence term that nudges the aggregated posterior toward the prior, sometimes replacing the KL with alternatives like MMB. The result is a latent representation that remains informative about the data while still supporting efficient inference. In short, info VAE aims to maintain a healthy flow of information through the bottleneck, improving both the usefulness of Z for downstream tasks and the diversity of generated samples. Third, VAE-GAN hybrids. These models fuse the VAE objective with adversarial training to boost sample quality. The decoder or generator is paired with a discriminator that learns to distinguish real data from reconstructions. The reconstruction loss is supplemented by an adversarial loss, encouraging outputs that look more realistic and sharp, often addressing the blurriness sometimes observed in vanilla VAEs. Training becomes more complex and can be less stable, So practitioners adopt stabilization strategies, careful balancing of generator and discriminator updates, gradient penalties, or two timescale optimization, for example. Finally, latent disentanglement. Beyond beta VAE, several approaches explicitly target independence among latent factors using penalties such as total correlation or alternative regularizers, factor VAE, TC VAE, etc. The goal is to have each latent dimension correspond to a meaningful independent factor of variation, enabling straightforward manipulation and interpretability. Evaluation often involves disentanglement metrics E, G, MIG-DCI alongside reconstruction and sample quality. Together, these variants illustrate how VAEs can be tuned to emphasize interpretability, information flow, or perceptual fidelity, depending on scientific goals and data constraints. Let me guide you through the core mechanics of a variational autoencoder, keeping our photo album and librarian metaphor, but sharpening it into a research-ready frame. Imagine a librarian who doesn't copy photos word for word, but instead distills their essence into compact, informative notes. In a VAE, that distillation is what the encoder does. The encoder reads the input data and produces two things at once. First, it gives us the parameters of a probability distribution that tells us where in latent space the data belongs. In most cases, this distribution is Gaussian, defined by a mean and a spread or variance. Instead of a single point, this acts like a small probabilistic node describing a region of latent space where good encodings live. That probabilistic framing is essential because it regularizes the encoding and makes the sampling process smoother and more meaningful. Second, the encoder supports sampling from that distribution, which is where the reparameterization trick comes in. Rather than directly sampling the latent code, we start with some standard random noise and then shift and scale it using the mean and variance from the encoder. This separation allows the whole process to remain differentiable, which means the network can be trained end to end. The decoder then does the opposite. It takes a latent point drawn from that encoded distribution and maps it back into the input space, producing a reconstruction. In simple terms, the decoder learns how to turn compressed codes back into full data. As training improves, those reconstructions look more and more like the originals. The latent space itself is a compact, structured neighborhood where similar inputs are stored close together. That continuity is powerful. It allows us to sample new points from the space to generate brand new data or to interpolate between points to create smooth transformations. For example, you could gradually morph an image of a cat into a dog, generating a whole sequence of believable intermediate images. In essence, the encoder, the decoder, and the latent space work together as a system, compressing, reconstructing, and generating data. Latent codes give us succinct descriptions of data, and the decoder turns them back into realistic outputs. This framework unlocks possibilities like denoising, filling in missing pieces, or inventing new variations, all by blending mathematical structure with intuitive creativity. On this slide, you will see the three key parts side by side: the encoder, the decoder, and the latent space. Together, they form a clear map of how information flows from inputs through compression to reconstruction and new generation. Before we dive deeper, here's a through line. Latent space is a map inside a model that compresses what we see into a tiny, navigable landscape. You can imagine sliders that change age, lighting, or style, producing plausible new images without touching the original data. This slide also sets up a key distinction: continuous latent spaces, like those in VAEs, let us blend features smoothly and explore new ideas by sampling from a probability distribution. Traditional autoencoders lock us into fixed codes, which makes exploring new variations harder. That difference matters for both creativity and reliability: smoother interpolation, better denoising, and more robust generation. In the upcoming slides, we'll compare how VAEs arrange information, why distribution matters, and what that implies for generating art, faces, and other data. Get ready to see how a well-shaped latent space unlocks flexible, realistic synthesis. Now, turning to latent space, I want to move beyond the idea that it's just a fancy file inside a model. Latent space is a coordinate map of the patterns a model has learned to organize in a compact, continuous form. It's not simply storing pixels, it's encoding the core features and relationships that define the data so you can navigate from one example to another by smoothly adjusting coordinates in that space. This is what makes latent representations so powerful for both compression and generation. One way to think about it is as a learned manifold, the essential structure of the data carved into a smaller, more manageable space. The goal is to keep the information that matters while discarding redundant detail. Because the space is continuous, small steps in latent coordinates translate into gradual, plausible changes in the output. This isn't just efficient storage, it's a practical engine for synthesis and exploration. How is this space learned? In common architectures, an encoder maps inputs to latent codes, and a decoder reconstructs the inputs from those codes. The training objective balances fidelity, how well the reconstruction matches the original, with the regularization that shapes the latent distribution. The model discovers features such as shapes, edges, textures, and colors, organizing them so that similar data points cluster together. The resulting latent code then guides how a new sample will look, even if that sample never existed in the training set. Visualize the space. We often project it into 2 or 3 axes. Those visualizations reveal a structured landscape where nearby points share meaningful features. The continuity is key. You can traverse the space with sliders or targeted guesses to create new images, test denoising options, or apply style changes. For example, in a set of facial images, moving along latent directions can adjust age, lighting, or a smile. Sampling new points by mixing features can yield fresh but believable faces. In handwriting tasks, you can morph one digit into another or adjust stroke thickness gradually. In photographs, you can shift a scene from daytime to dusk in a smooth interpolation. Latent space serves dual roles. It compresses data into a compact representation and enables creative generation. It also supports practical tasks such as denoising and data augmentation, which can improve learning in downstream models. Of course, these spaces are learned from data and may entangle features or reflect biases in the training set, so interpretation and careful evaluation remain important. Still, latent space provides a cohesive framework for understanding and shaping data through a single, navigable landscape. Let's use this slide to push beyond the basics and think about how the latent space is shaped, not just what it looks like. In a VAE, the latent space is not a rigid map but a continuous, probabilistic one. We don't store a single code per image, we learn a distribution over codes, typically centered around a normal prior. This makes the space smooth and navigable. Small moves in latent coordinates tend to produce gradual changes in the decoded output, while sampling from the prior lets us generate genuinely novel instances. By contrast, a traditional autoencoder fixes a code after training with limited regularization or structure to guide exploration. That fixed code often yields brittle generalization and limited ability to interpolate or extrapolate between factors of variation. Because the VAE enforces a distribution over latent variables, the geometry of the space becomes meaningful. Regions of the latent space have different likelihoods under the prior. So high-density areas correspond to plausible factors of variation, while low-density regions reward careful exploration. This is what enables control generation. You can sample, you can interpolate between samples, and you can blend attributes like pose, style, or lighting in a continuous way. But not all continuous latent spaces are created equal for learning disentangled factors. This leads to several important variants. First, beta VA, where we amplify the KL term by a factor beta is greater than 1. The intuition is simple. Stronger pressure to match the prior encourages the latent factors to separate into independent interpretable dimensions. The payoff is often clearer disentanglement, but at the cost of reconstruction fidelity. In practice, you trade off. You gain interpretability and smoother factor control at the risk of blurrier reconstructions if the model capacity or data are insufficient. InfoVIA offers a different maneuver. Rather than merely shrinking the posterior toward the prior, InfoVAE rebalances the objective to preserve informative structure in the latent codes. Techniques such as alternative divergences or MMD penalties allow us to control how much information the latent representation retains about the input, mitigating posterior collapse while maintaining useful structure for generation and downstream tasks. Hybrid approaches like VAO GANs push further on sample quality. Here, the VAE decoder is paired with a GAN discriminator, guiding the decoder to produce sharper, more realistic samples while still maintaining a latent structure. The result can be a more faithful synthesis without abandoning the advantages of a continuous, structured latent space. Disentanglement focused variance, factor VAE, DIP VAE, and related metrics like MIG or SAP explicitly penalize residual dependence among latent factors, often via total correlation penalties. The goal is a latent code where each dimension corresponds to an interpretable factor of variation. Next, we pull back the curtain on what these models actually learn. Rather than a single answer, they map data into a space of possibilities, a probabilistic view that lets us generate new samples that still feel familiar. We'll zoom in on variational autoencoders, where encoding is not a fixed point but a distribution over hidden factors. You'll hear about latent variables, the knobs you turn to shape, style, lighting, and pose, and how sampling from their distributions yields fresh, plausible images. We'll discuss training goals, steer outputs toward real data while keeping the latent space from memorizing, so generation stays flexible. Why probability matters. It handles uncertainty, supports inference, and helps flag anomalies. Finally, we'll unpack mean and variance, how they define each latent distribution and enable diverse, robust generation for downstream tasks. Generative models give us a way to learn the data distribution so we can synthesize new samples that are plausible extensions of what we've seen. They don't just imitate, they model the underlying structure, the recurring patterns, the variability, and the limits of what's possible within the data. That capability underpins tasks from image synthesis to anomaly detection, and it provides a probabilistic lens through which we can reason about data, what is typical and what could be. Variational autoencoders, or VAEs, embody this probabilistic approach. Instead of encoding an input into a single fixed code, as in deterministic autoencoders, VAEs encode inputs as distributions. In practice, this means we represent each input by a range of plausible latent factors, a distribution over latent variables rather than a single point. The key virtue is that this captures uncertainty explicitly and enables generative sampling. By drawing from the latent distribution, we can produce new examples that still look like they belong to the same data family. A handy intuition is to think of latent variables as hidden factors that shape the observed data, for example, style, lighting, and pose in images. These latent factors vary continuously and can be turned by sampling from their distribution. By sampling different values, the decoder can generate new images that maintain realism while exploring variation within the learned manifold. Training a VAE involves a careful balance. We push the reconstructions toward the real data, so samples look plausible, but we also regularize the encoding so it stays close to a chosen pair. This discourages memorization and fosters a structured latent space that supports meaningful interpolation and sampling. In concrete terms, the model learns an approximate posterior distribution, QZ vertical bar X, and a prior PZ, and it optimizes an objective that combines reconstruction quality with a penalty that aligns QZ vertical bar X with PZ. This is often implemented as a form of the evidence lower bound or elbow, which couples learning about the data with regularization that preserves generative capabilities. Why does probability matter here? It gives us principled uncertainty handling, robust inference for missing factors, and flexible generation. The latent variable formulation captures multiple plausible explanations for each input, so generation isn't tied to a single correct answer. It also supports anomaly detection. Data that lie in regions of unusually low likelihood under the learned model can be flagged as atypical. As a practical workflow, you typically start by learning the typical shapes and colors in your data, then map out the variations that could appear, and finally generate and assess new samples. The feedback loop, generate, evaluate, refine, helps the model improve over iterations. In research contexts, VAEs open avenues for art, science, and interactive design, enabling exploration of design spaces, unsupervised representation learning, and data-driven experimentation across disciplines. Building on the idea that the encoder maps each input to a distribution over latent factors, we can push this framework further by shaping not just what we encode, but how we organize and interpret the latent space. A family of approaches centers on disentanglement, making individual latent dimensions capture more or less independent factors of variation, such as style, stroke, or lighting, rather than entangled mixtures. Let me outline a few prominent directions and what they bias. First, beta VAE. Here, we explicitly tune the balance between reconstruction and regularization by introducing a weighting parameter beta on the KL divergence term. The objective becomes a reconstruction term minus beta times KLQ vertical bar X vertical bar BZ. With beta greater than 1, the model is encouraged to learn more factorized, interpretable latent factors at the expense of a bit of reconstruction detail. Practically, this yields more disentangled representations factors that align with distinct generative aspects of the data, for example, stroke thickness versus curvature in digits or pose versus lighting in faces. The trade-off is real. Too large a beta can blur details or limit expressiveness. So many practitioners adopt a gradually increasing capacity or an annealed beta schedule to start with faithful reconstructions and gradually encourage disentanglement. Second, Info VAE. This variant reframes the regularizer to preserve information about the inputs in the latent code while still discouraging over-reliance on the prior. In short, it seeks to maximize the mutual information between X and Z, so the latent code remains informative about the data while controlling the aggregated posterior mismatch with the prior. The upshot is more informative latent representations that still stay well-behaved and less prone to posterior collapse, a common pitfall in vanilla VAEs. Third, VAE-GAN hybrids. By pairing a VAE with adversarial training, we can keep the probabilistic benefits of a latent distribution while enjoying the sharper, more realistic reconstructions typical of GANs. In practice, the decoder is trained both to reconstruct inputs and to fool a discriminator that tries to distinguish real samples from reconstructions. This often yields crisper textures and better perceptual quality, though it introduces training complexities and new hyperparameters to balance reconstruction, KL, and adversarial objectives. Finally, latent disentanglement with structured priors. Beyond beta VAE, approaches like factorized priors or total correlation penalties, often in variants such as factor VAE or TC regularized VAEs, explicitly penalize dependencies among latent units. This nudges the latent codes toward independence, enabling more interpretable access of variation and facilitating downstream tasks such as controllable generation or domain adaptation. Evaluation typically involves metrics like MIG, DCI, or SAP, and we must remain mindful of the trade-off between disentanglement and reconstruction fidelity. Next, we pull back the curtain on reconstruction. Think of turning a full image, sound, or sentence into a compact fingerprint, and then rebuilding it from that fingerprint. An encoder sketches a latent space, the hidden code that captures the essential ideas, and a decoder uses that code to recreate the data. The aim is to minimize the gap between original and rebuilt data, so the latent space holds meaningful structure rather than noise. We'll see how we measure success: mean squared error for numeric fidelity, and binary cross entropy for yes divided by no decisions on each bit or pixel. But reconstruction alone can overfit, so regularization guides the latent space toward a simple, smooth prior. We balance reconstruction accuracy with staying close to the prior, which helps with generalization and meaningful interpolation between ideas. Then we'll preview how these ideas let us generate new, plausible samples from a learned latent map. The reconstruction paradigm, at its core, is remarkably simple but profoundly powerful for learning machines. A model learns to recreate the original input from a compact representation tucked away in a latent space. The encoder transforms the input into a lower dimensional, meaningful summary, and the decoder uses that code to rebuild the data, be it an image, a sound, or a sentence. The objective is to minimize the gap between the original data and its reconstruction. When that gap is small, we infer that the latent code has captured the essential structure and content of the input. From a practical standpoint, the process starts with an input that the encoder compresses into a latent map. The decoder then expands that map back into a full version of the data. The central challenge is to preserve the important details while discarding the noise and nuisance variation that do not contribute to the underlying structure. A high-quality reconstruction signals that the model has learned a useful representation, one that generalizes beyond the exact training instances and supports meaningful manipulation in the latent space. How do we judge reconstruction quality? Two widely used guides anchor practice. Mean squared error assesses how far predicted values are from the true ones by averaging the squared differences across data points. Binary cross entropy is appropriate when targets are binary or probabilistic, evaluating the model's confidence in its yes divided by no decisions. Taken together, these metrics provide a practical readout of reconstruction fidelity. Of course, they are not perfect proxies for all aspects of perceptual or task-relevant quality. In image work, for example, small MSE gains may not translate to perceived improvements, so researchers often supplement with perceptual losses, feature-based criteria, or domain-specific metrics such as SSIM, depending on the application. Conceptually, the big idea is to cultivate a latent representation that is not merely a compressed copy but a meaningful, usable summary of the data. If one can redraw the input faithfully from the latent code, the space becomes a playground for interpolation, attribute manipulation, and generative sampling. An intuitive way to see it is to imagine turning a complex scene into a few essential nodes, then reconstructing the full scene from those nodes. If the reconstruction remains faithful, the nodes captured the right ideas. Building on the idea that regularization guides how the latent space behaves, we can tune what we want that space to prioritize. In contemporary work, several calibrated extensions push beyond the vanilla KL penalty to shape the geometry, the information content, and even the perceptual quality of generated data. I'll outline a few representative directions and why they matter for researchers aiming at robust, disentangled representations. First, beta VAE. Here, we scale the KL term by a factor beta is greater than 1. The intuition is simple. By increasing the pressure to match the prior, we encourage the latent factors to become more independent and disentangled. The consequence is a latent space where axes tend to capture separate generative factors. The trade-off is explicit. Reconstruction fidelity can suffer if the capacity to represent fine detail is curbed too aggressively. A practical remedy is to manage capacity, gradually increasing beta or starting with a lower beta and annealing it to a higher value during training. This annealing helps preserve enough reconstruction detail while still steering the factors toward modularity. Second, info VAE variants reframe the objective to balance information preservation with regularization in a more flexible way. Instead of forcing the posterior to resemble a fixed prior too aggressively, info VAE formulations can incorporate a mutual information term or use alternative divergences and priors. The payoff is that we can retain meaningful content in the latent codes while maintaining a structured, generative prior, mitigating issues like posterior collapse that sometimes plague standard VAEs under strong regularization. Third, VAE GAN hybrids integrate an adversarial discriminator to improve sample realism while preserving a probabilistic latent structure. The GAN component pushes the decoder toward producing sharper, more plausible outputs, addressing the often observed blur in VAE reconstructions. The challenge is to balance the adversarial loss with the Bayesian reconstruction and KL terms so that the latent space remains informative and navigable rather than being overwhelmed by the discriminator. On the disentanglement front, several regularizers target latent dependency directly. Total correlation penalties, as used in factor VAE and related approaches, explicitly discourage dependencies among latent dimensions. Other variants, DIP-VAE, TC-VAE, combine reconstruction with disentangling constraints to encourage factors that vary independently across data. Evaluation then hinges on metrics that quantify factor independence and alignment with ground truth generative factors. Finally, practical choices matter. The prior distribution, isotropic Gaussian versus learned priors such as VAMP prior or mixers, capacity scheduling, and training stability all influence outcomes. In sum, regularization in VAEs is not a single knob but a family of strategies to trade off accuracy, stability, and interpretability of the latent space. Properly calibrated, these methods yield latent representations that interpolate smoothly, generalize better, and support more controllable generation across modalities. This is where regularization truly becomes a driver of both reliable reconstruction and imaginative yet plausible generative modeling. Next, we pull back the curtain on a clever trick that keeps gradients on track even when randomness is involved. We'll connect the dots between sampling and learning, showing why vanilla randomness can stall training and how the reparameterization trick separates the noise from the parameters so the network can still learn. We'll walk through how encoders predict mean and width, how latent variables are formed by shifting and scaling, and why this yields smoother, faster optimization across large models. Then we'll sketch the practical benefits end-to-end training, reduced gradient variance, and better representations across images, text, and audio. Finally, a quick analogy to keep the idea tangible before we dive into equations in the next slides. Get ready to see the math become practical. Beyond the core reparameterization trick, the VAE family has evolved to give us finer control over the latent space and the quality of reconstructions. Let me outline a few directions that researchers often pursue when aiming for disentangled representations and sharper generative outputs. First, beta VAE. The core idea is simple yet powerful. Put extra emphasis on the regularization term during training. When you increase this pressure, the model is encouraged to use fewer latent factors more independently, which often leads to more disentangled representations. The trade-off, however, is that reconstruction quality can decrease since the model sacrifices some detail for independence. To manage this, researchers often apply a warm-up schedule, gradually increasing the regularization strength to smooth the transition and avoid sudden drops in reconstruction fidelity. Second, Info VAE. This approach tweaks the training objective so that the latent code stays more informative about the input while still being guided toward the prior distribution. In effect, it ensures that the model doesn't collapse into uninformative latents. The result is a representation that is both meaningful and robust, helping maintain generation quality even in deeper or more complex networks. Third, VAE GAN hybrids. Here, the strength of VAE's probabilistic learning is combined with the sharpness of GANs. The VAE structure of encoder and decoder is complemented by a discriminator that judges how realistic the outputs look. This adversarial feedback helps generate much sharper, more detailed images than a standard VAE would produce. The trade-off is that training becomes trickier and less stable, so it often requires careful balancing of the different losses and sometimes staged training strategies. Finally, we have methods focused on latent disentanglement beyond beta VAE. These approaches directly penalize dependencies between latent factors, ensuring they remain independent and interpretable. Techniques like factor VAE and beta TCVAE work along these lines, and researchers evaluate their success using disentanglement metrics that measure how cleanly individual latent variables capture distinct aspects of the data. Let me outline the core idea here and why it matters for learning compact representations. In many generative models, the hidden code that represents a data point depends on randomness. If we just sample that code directly during training, the randomness breaks the smooth flow of gradients, making learning unstable and noisy. The reparameterization trick solves this by rewriting the sampling in a way that separates the randomness from the learnable parts of the model, while still keeping the entire process trainable end to end. The idea is straightforward. First, randomness is drawn from a separate, simple distribution, a kind of baseline noise. This noise becomes the only source of uncertainty for a given training pass. Next, the network's encoder takes the input and produces parameters. Think of them as knobs to shift and scale the noise. The latent code is then created by combining the noise with those parameters in a fixed, differentiable way. Because the process is deterministic, once the noise is chosen, the gradients can pass cleanly through it during training. The practical effect is that sampling becomes predictable and trainable. We've separated the uncertainty from the learnable parts, so the optimization process doesn't get disrupted. This gives a smoother learning signal and usually leads to faster and more stable training of variational autoencoders, which depend on passing information through a stochastic bottleneck. A helpful analogy is cooking. Imagine following a recipe but adding a pinch of salt each time, scooped randomly from a bag. The pinch of salt is the randomness, the recipe is the deterministic rule, and the final taste is like the latent code. The network learns recipes that consistently produce good dishes, while the randomness of the salt is handled separately. In practice, this means the model avoids chasing randomness directly. Instead, the randomness is external, while the math remains clean and trainable. The outcome is faster convergence on large datasets and clearer insight into what the model learns to reconstruct or generate. Although we usually explain this in terms of images, the same principle works for text, sound, or any data. This trick is the cornerstone that makes variational autoencoders possible, allowing them to create new, realistic examples from learned memory while handling randomness in a controlled and differentiable way. Having covered the reparameterization trick, we can now turn to how researchers push VAEs beyond vanilla formulations to achieve disentangled latent structure and higher fidelity generation. I'll outline several productive directions and what they bias, along with practical caveats. First, beta VAE and disentanglement. In beta VAE, we multiply the KL term by a factor beta greater than 1. This intensifies the information bottleneck, encouraging the encoder to capture only the most essential factors of variation in the latent codes. The payoff is often better disentanglement. Individual latent dimensions align with interpretable factors such as pose, lighting, or object identity. The catch is a potential drop in reconstruction quality and even posterior collapse if beta is too aggressive. The standard remedy is to balance beta with model capacity and training dynamics, often via KL, annealing gradually increasing beta during training, or a controlled capacity term that widens the bottleneck as training progresses. Second, Info VAE and preserving useful information. Info VAE reframes the objective so we don't overprune the latent representation. Rather than forcing the aggregate posterior to align with the fixed prior too aggressively, Info VAE encourages sufficient mutual information between X and Z while still regularizing the latent distribution. In practice, this can be realized with flexible divergences, for example, incorporating MMD or related terms, and a targeted balance between reconstruction, regularization, and information preservation. The result is encodings that remain informative for reconstruction and downstream tasks, with reduced risk of severe posterior collapse and sometimes improved sample quality. Third, VAE Gantt hybrids for sharper samples. Here we bring in an adversarial discriminator alongside the VAE objective. The decoder is trained not only to reconstruct faithfully but also to fool the discriminator, which pushes generated samples toward the realism of actual data. The reparameterization trick is still essential because sampling from QZ vertical bar X feeds the generator. Hybrid training can yield crisper, more globally coherent images or sounds, but it introduces training instability and requires careful balancing of the VAE loss and the adversarial loss E.g. through architectural choices, loss weighting, or staged training. Fourth, latent disentanglement with advanced priors and objectives. Beyond beta VAE, methods like beta TCVAE penalize the total correlation of the latent distribution to promote independent factors of variation. Other approaches impose structured priors or factorized latent schemas to capture separate interpretable factors. Evaluation becomes crucial. Metrics like MIG or SAP help quantify disentanglement, but we should remember the trade-off. Increasing disentanglement often competes with reconstruction fidelity and demands suitable data and inductive biases. Now that we've mapped how VAEs encode data and wander through a stochastic latent space, the focus shifts to reconstruction, the art of turning hidden codes back into something we can see, hear, or read. We'll compare decoding approaches: deterministic decoders that reproduce a single output, probabilistic decoders that add realistic variation, autoregressive and hierarchical decoders that build detail step by step. We link these choices to data types: images with Gaussian likelihood, binary data with Bernoulli, and categorical data with a multinomial likelihood. You'll also see how post-processing, denoising, and sharpening improves realism without washing out structure. Finally, practical notes: when to prefer speed over fidelity, how the mean path versus sampling affects testing, and the balance between reconstruction quality, KL terms, and compute. By the end, you'll have a clear map of decoding design for VAEs. Beyond the basic encoder-decoder scaffold, researchers have developed a family of variants that tune the latent space for different goals, disentanglement, realism, and flexibility across data modalities. First, beta VAE and friends. By introducing a scaling factor beta on the KL term, beta VAE encourages the model to use fewer, more independent latent factors. In practice, beta values greater than 1 typically promote disentanglement, making individual latent dimensions correspond to interpretable generative factors such as pose, lighting, or texture in images. The trade-off is clear. Reconstruction fidelity can degrade as beta increases, so practitioners often employ annealing schedules or warm-up ramps to balance learning. Beta VAE set the stage for systematic exploration of disentangled representations and sparked a broader line of work on quantifying disentanglement. Second, Info VAE and related objective modifications. Instead of a strict KL match to a fixed prior, Info VAE emphasizes preserving meaningful mutual information between inputs and latents while allowing more flexible priors. The result is a model that can reuse latent capacity more effectively and resist posterior collapse, especially in powerful decoders. In short, you get richer latent codes without sacrificing the stability of optimization, provided the objective terms are balanced carefully. Third, VAE-GAN hybrids. Hybrid architectures pair the VAE's probabilistic encoding with a GAN's adversarial objective to sharpen reconstructions and produce more realistic samples. The decoder is guided not only by pixel-wise or perceptual reconstruction losses, but also by a discriminator that rewards realism. This often yields crisper images and more detailed textures, but it introduces training instability and requires careful balancing of the reconstruction and adversarial losses along with regularization techniques to keep the latent space well behaved. Fourth, latent disentanglement and structure. Beyond beta VAE, several approaches impose penalties on total correlation or use learnable priors to encourage factorization of the latent space, factor VAE, VAM prior, and similar schemes. Hierarchical or multi-level VAEs extend the idea by placing latent variables at multiple scales or depths, enabling the model to capture coarse to fine structure useful for complex images or long sequences. In sequential domains, sequential VAEs and related models blend temporal dynamics into the latent hierarchy, aligning with order and timing in the data. Finally, practical design tips. Match the encoder divided by decoder family to data types connets for images, recurrent or transformer style encoders for sequences, and be mindful of capacity versus regularization. Employ warm-up schedules for KL terms, monitor latent traversals, and use appropriate metrics for disentanglement and sample quality. These variants expand what VAEs can express, enabling researchers to tailor models for interpretability, realism, or multiscale representations. Beyond the basic sampling mechanism, there is a whole family of objectives and architectures that shape how latent factors organize themselves, how much information is preserved, and how realistic the reconstructions look. Here are some directions researchers actively pursue. First, beta-wise. The main idea is to adjust the strength of the regularization term that pushes the latent representation toward a simple prior distribution. When we increase this regularization using a higher beta value, we encourage the model to learn more independent and disentangle latent factors. The trade-off is that while the latent space becomes cleaner and easier to interpret, the reconstructions may lose some detail or accuracy. In practice, this often yields more interpretable latent axis, one axis aligning with stroke width, another with digit slant, etc. But it can require careful training, such as annealing beta or moderating a capacity constraint, so that the model first learns to encode information and then gradually organizes it into independent factors. Second, info VAE. This line argues for a more information-friendly regularization than the vanilla KL penalty. By relaxing or reformulating the divergence term, for example, using flexible divergences like MMD, or introducing a controlled capacity term that targets the aggregated posterior, Info VAE aims to preserve more mutual information between X and Z and avoid posterior collapse. The practical upshot is richer latent usage and often sharper reconstructions, while still maintaining a meaningful prior geometry. Third, VAE-GAN hybrids. Here, the generation pathway is augmented with an adversarial objective. The encoder-decoder pair produces reconstructions that must both resemble the input and fool a discriminator into believing they are real. The GAN signal sharpens details and textures, addressing a common weakness of VAE's blurry samples. The trade-off is training complexity and stability. Balancing the adversarial loss with the reconstruction and regularization terms requires careful scheduling, sometimes using separate optimizers, gradient penalties, or Wasserstein-style losses to keep training tractable. Fourth, explicit disentanglement strategy. Methods like factor VAE and beta TCVAE add penalties that target the total correlation among latent variables, pushing the joint distribution toward a product of marginals. In effect, they explicitly discourage latent coordinates from leaking information about one another, promoting independent factors. Evaluating disentanglement often involves metrics that probe factor alignment with generative factors, and practitioners must navigate the trade-off between disentanglement and reconstruction quality. Practical takeaways across these approaches: monitor information flow to the latent space, use annealing or capacity control to stabilize training, and consider vectorized sampling to keep inference efficient. When you want variety at test time, sampling remains attractive. When you want stable, deterministic reconstructions, the mean route can be preferable. Each variant trades reconstruction fidelity, latent usage, and sample realism in different ways, so the choice depends on your research question and downstream application. Today, we turn our attention to the reconstruction stage in variational autoencoders. how the latent code is turned back into observable data. The core question is the nature of the decoder Pxn vertical bar z and how its design shapes the quality, realism, and efficiency of reconstructions. We can think of decoding as a spectrum of strategies, each with its own trade-offs. First, deterministic decoders. Here, the mapping from z to x is fixed. For a given latent code, you obtain exactly one output. This yields fast, stable reconstructions and is appealing when speed and reproducibility are priorities. The downside is a potential lack of realism, as there is no mechanism to account for natural variability in real data. Second, probabilistic decoders. These models output a distribution over x instead of a single point. Sampling from Px vertical bar z can produce outputs that are similar yet not identical, injecting natural variation and improving realism. This probabilistic stance is particularly valuable when data exhibit intrinsic stochasticity or when we wish to capture uncertainty in generation. Third, autoregressive models. In these decoders, the output is built piece by piece, with each new element conditioned on previous ones. This approach excels at capturing local dependencies and long-range structure, making it well suited for textures, time series, and audio where sequential coherence matters. The price is higher computational cost and slower generation, especially for long sequences. Fourth, hierarchical structures. These decoders organize latent information across multiple levels. Higher levels encode broad structure and global semantics, while lower levels refine details and textures. This separation can improve both global consistency and local fidelity, but it introduces architectural complexity and requires careful training to ensure the hierarchy is properly utilized. These options impose a trade-off between reconstruction accuracy and computation time. They also interact with data type, which determines the appropriate likelihood model. For continuous data, G. Smooth image intensities. A Gaussian likelihood is common. For binary data, a Bernoulli likelihood is natural, and for data with multiple categories, a categorical likelihood is used. The chosen likelihood shapes training signals and ultimately what the reconstructions look like. Post-processing offers a practical lever to improve quality after decoding. Denoising reduces random specs, sharpening enhances edges. The goal is to reduce artifacts without altering the core content generated by the model. In practice, apply post-processing judiciously. Excessive smoothing can erase important details, while insufficient cleaning may leave distracting artifacts. Finally, translate these choices into practice. If speed matters, lean deterministic decoders. If variety and realism are priorities, probabilistic decoders offer benefits. For long sequences, autoregressive decoders shine. For a balance of global structure and fine detail, hierarchical decoders are advantageous. Always consider data size and compute power, and iterate with careful ablation. Simple decoders for core regions, more expressive ones where fidelity is critical. The overarching aim is to improve how models copy reality reconstructions that are both faithful and credible. Up next, we zoom from the idea of a latent space to the engine behind VAEs, how they compress complex data into a small, meaningful set of numbers and then reconstruct plausible variants. We'll see how this dual task, compressing and recreating, lets a single model imagine many new pictures, sentences, or sounds that still feel real. In the slides ahead, we explore three applications: crisp, varied visuals and higher resolution images, natural sounding text and diverse voices, and safe, synthetic data to train other systems while protecting privacy. You'll hear how VAEs use a probabilistic map moving around the latent space to generate smooth, believable changes. We also cover anomaly detection, spotting outliers via reconstruction error and practical trade-offs, data needs, compute, and ethical considerations. By the end, you'll see why VAEs are both powerful and nuanced. Building on the capabilities you summarized, researchers have pushed VAEs toward more controllable, sharper, and more informative generations by combining them with targeted objectives and architectural hybrids. Let me walk you through a few of these directions that are particularly impactful for researchers. First, beta VAE. By inflating the weight on the KL divergence term, beta VAEs encourage the latent factors to align with independent, interpretable factors in the data. In effect, you trade some reconstruction fidelity for disentangled representations, where changing one latent dimension tends to modulate a single concept pose, lighting, texture, or shape in a predictable way. This is powerful for controllable synthesis and for downstream tasks like data augmentation with interpretable variations. The trade-off is real reconstruction quality can degrade if beta is too large. So practitioners typically seek a sweet spot and often combine it with carefully designed architectures or regularizers. Second, InfoVAE variance. Here the objective re-emphasizes information preservation between latents and data, reducing issues like posterior collapse that can plague standard VAEs when decoders are very expressive. By reconfiguring the regularization to preserve mutual information or by using alternative divergences, InfoVAE aims to keep latents informative without sacrificing too much reconstruction. The result can be more usable latent codes for downstream analysis or conditional generation, especially in context where interpretability and reliability of the latent space matter. Third, VAE-GAN hybrids. These marry the probabilistic reconstruction of VAEs with the sharpness incentives of GANs. The decoder learns to produce realistic samples, while a discriminator guides realism through adversarial feedback. The net effect is often crisper textures, more faithful edges, and better high-frequency detail than vanilla VAEs. However, training can be more delicate, requiring balanced weighting of reconstruction, KL, and adversarial losses, and sometimes stabilization techniques. Disentanglement and control generation extend beyond beta VAE. Variants like factor VAE or deep VAE explicitly target total correlation or distributional constraints to promote independent factors, enabling more robust, interpretable control over generated content. In practice, you might condition a model on few known factors, style, class, condition, and still enjoy the benefits of a solid latent space. Building on the idea that VAEs learn a compact latent space, we can turn to a family of variants that refine what that space encodes and how sharply the model trades off reconstruction against generative realism. First, beta VAE and disentangled representations. The core idea is to adjust the information bottleneck by weighting the KL term with a factor beta. When beta is greater than 1, the model is more strongly constrained to match a simple prior, which often leads to more independent, interpretable latent factors. In practice, this can yield disentangled dimensions, one latent unique capturing pose, another lighting, another texture, and so on. The trade-off is clear. You typically see a modest drop in pixel-wise reconstruction quality in exchange for more controllable fact-priced latent access. Techniques such as KL, annealing, ramping beta up during training help balance learning useful factors early with stronger regularization later. This line of work directly targets interpretability and controllability of the latent space, which is invaluable for downstream reasoning, manipulation, and transfer across related datasets. Next, InfoVAE. Rather than forcing the posterior to match a fixed prior with a strict KL penalty, InfoVAE rebalances terms to preserve information about the input while still regularizing the latent distribution. The objective includes a mutual information-like term between input and latent, ensuring that the latent carries meaningful content, combined with a penalty that controls distributional mismatch. The practical upshot is more faithful reconstructions and richer, information-rich latent codes without collapsing into overly simplistic priors. This can mitigate some of the posterior collapse concerns that sometimes plague vanilla VAEs when modeling complex data. On to VAE-GAN hybrids. Here we pair the VAE with an adversarial discriminator so the decoder not only minimizes reconstruction error but also fools a critic that judges realism. The GAN-like loss encourages sharper textures and more realistic details, often producing higher quality images than a standard VAE alone. The challenge is balancing the adversarial objective with the probabilistic training of the VAE. Instability can arise, so careful scheduling and loss weighting are key. When done well, you get the best of both worlds, a probabilistic tractable latent model with perceptually convincing generations. Finally, latent disentanglement and related strategies. Beyond beta VAE, methods like factor VAE and DIP VAE explicitly penalize dependence among latent channels e.g. via total correlation penalties to promote independence that aligns with interpretable factors of variation. Evaluation often uses synthetic datasets with known factors to quantify how well each latent dimension corresponds to a factor. In practice, these approaches enable targeted interventions in the latent space, adjusting pose, style, or modality in a controlled way while maintaining plausible, high-quality generations. Building on the VAE-based anomaly detector, we can leverage several extensions that push beyond simple reconstruction errors to improve robustness, interpretability, and sensitivity to subtle deviations. First, consider beta VAE and latent disentanglement. By introducing a beta parameter in the elbow with beta is greater than 1, we encourage the model to learn a more factorized latent representation. This can be transformative for anomaly detection. When an outlier activates a rare combination of latent factors, we can point to specific dimensions as the source of the abnormality. In practice, increasing beta trades off reconstruction fidelity for disentanglement, so one must tune beta carefully. The payoff is interpretable explanations for why something is flagged, not just that it is unusual. Second, InfoVAE offers a targeted remedy to a common pitfall: mismatch between the prior and the learned posterior. InfoVAE adjusts the objective to preserve more information about the input in the latent code, reducing posterior collapse and yielding better calibrated anomaly scores. The result is a latent space that more faithfully encodes the structure of normal data, thereby enhancing the separation between normal variation and true anomalies, especially when normal data occupy a broad manifold. Third, VAE-GAN hybrids combine the probabilistic reconstruction of VAEs with the adversarial realism of GANs. The decoder is trained with a GAN loss in addition to reconstruction loss, producing sharper, more plausible reconstructions. This is particularly valuable for image or spectrogram-like data where pixel-level errors can be misleading. A realistic reconstruction makes deviations, subtle textures, fine-grained patterns more detectable as elevated reconstruction or perceptual errors. The caveat is training stability, so practitioners often adopt stabilized GAN objectives, feature matching, or patch-based discriminators. Turning to practical scoring, many researchers augment the reconstruction error with latent space likelihoods or density estimates. A two-channel score, how well X fits the latent prior and how plausible the latent encoding is, can reduce false alarms from benign high variance patterns. Disentangle latents further help by isolating which factors drift in an anomaly, aiding downstream investigation or triage. Finally, for sequential data, temporal VAEs or autoregressive decoders capture dynamics that static VAEs miss, improving detection of anomalous trajectories. Faster, more robust variants A. G. Robust VAEs, flow-based posteriors, further enhance reliability in real-world streams. In short, these directions, disentanglement, information-rich posteriors, and perceptually guided reconstructions offer principal routes to more accurate, interpretable, and actionable anomaly detection in complex data. Now that we've framed VAEs at a high level, let's move into the practical hurdles you'll encounter during training. I'll preview 3 bottlenecks: blur from pixel-wise loss, limited diversity due to mode collapse, and the tight balance between regularization and reconstruction that can even cause posterior collapse. We'll talk about why clear, varied samples matter for downstream tasks and how teams diagnose these issues as training unfolds. Next, we'll peek under the hood of the latent space. Latent representations are powerful but tangled, so researchers pursue disentanglement, stronger interpretability, and occasional domain-guided priors to keep features understandable and editable. Finally, we'll address the cost side: training time and resources. We'll survey tricks to speed things up: faster sampling, pruning, discrete latents, and flow-based alternatives, and discuss how to pick the right approach for your task and data. Building on the 3 core issues you highlighted: blur, lack of diversity, and the regularization reconstruction balance, there are well-established directions to push VAEs toward better fidelity and richer latent structure. I'll outline several key variants and how they address these challenges with practical takeaways for researchers. First, beta VAE and latent disentanglement. In beta VAE, we scale the KL term by a factor beta is greater than 1. This strengthens regularization, nudging the encoder to produce a simpler, more factorized latent distribution, and, as a side effect, encourages disentangled factors of variation. The payoff is interpretable controls over generated content A. G. Pose, lighting, stroke style, and smoother latent traversals. The trade-off is reconstruction quality. Pushing beta too high can blur details and hurt fidelity. In practice, start with beta modestly above 1 and investigate a targeted increase only for factors you want to disentangle. For stronger disentanglement, while preserving fidelity, variants like factor VAE or dip VAE add a total correlation penalty or distribution matching constraints that promote independence among latent dimensions without blindly sacrificing reconstruction. Second, info VAE. This family revises the objective to avoid diminishing information in the latent code while still reigning in the posterior. By reweighting or replacing the KL term with alternatives A, G, MMD-based divergences are information-centric penalties. InfoVAE maintains a richer latent representation and mitigates posterior collapse. The practical gain is retaining useful latent information even when enforcing regularization, which helps both reconstruction detail and downstream tasks that rely on meaningful latent factors. The caveat is that you must choose and tune the alternative divergence carefully as it shapes the information bottleneck differently from standard KL. Third, VAE GAN hybrids. By pairing a VAE with a GAN discriminator, you can dramatically improve perceptual sharpness and texture fidelity while preserving probabilistic modeling. The decoder benefits from adversarial feedback that emphasizes realistic, high-frequency structure, addressing the blur problem more directly than pixel-wise losses alone. However, training stability becomes a concern. Balancing the VAE objective, the GAN loss, and the KL term requires careful scheduling A. G. Alternating optimization, weighted losses, or perceptual losses. When done well, you get crisper samples with richer detail and still a usable latent space. Fourth, latent disentanglement focused approaches. Beyond beta, these methods explicitly aim to factorize the latent space so components correspond to independent factors of variation. Techniques enforce total correlation penalties, use joint training with auxiliary objectives, or design prayers that promote independence. Benefits include more controllable generation and meaningful traversals. Risks involve misalignment between statistical disentanglement and human interpretable semantics, and sometimes slower convergence. Practical takeaways: use stage training, KL annealing, free bits, augment data to encourage robust features, monitor both reconstruction quality and diversity, and evaluate with latent traversals, FID divided by LP-IPS where appropriate, and qualitative checks. These variants aren't mutually exclusive hybrid setups combining disentanglement objectives with perceptual losses and tempered regularization are increasingly common in high-fidelity, controllable generative modeling. Latent representations in VAEs are the hidden coordinates the model uses to describe data, but their practical meaning is often elusive. To move beyond the basic idea of a Z-vector encodes factors of variation, researchers are pursuing three interlocking directions that push latent space toward interpretability without sacrificing performance. First, disentangled representations. The goal is for each latent dimension to correspond to a distinct, independent factor so color can be captured without changing shape, and size or texture can vary independently. This is where beta VAE and its successors come in. By weighting the regularization term beta is greater than 1, the model is nudged toward factoring information across dimensions, reducing entanglement. Extensions like factor VAE and deep VAE add explicit penalties for remaining dependencies, total correlation penalties, or statistical decoupling of encoder outputs to encourage more orthogonal human interpretable factors. Practically, disentanglement enables straightforward latent traversals. Tweaking one latent coordinate yields a predictable, isolated change in the output, which is crucial for editing, evaluation, and transfer to new tasks. It is also where researchers deploy latent space traversals and quantitative disentanglement metrics to assess progress. Second, enhanced regularization strategies. Regularization is the compass that guides latent variables during training. Beyond fixed beta terms, InfoVAE and related approaches enforce informative yet compact representations by balancing reconstruction quality, mutual information between inputs and latents, and prior conformity. Some methods employ learned priors or adversarial components to shape the latent distribution more flexibly. The key idea is to steer the encoder toward factors that are stable and reusable across data instances, improving predictability and editability. It's a delicate balance. Too aggressive regularization can erode realism, while too weak regularization leaves entanglement and ambiguity in place. The right regularization makes the latent space easier to read and to manipulate downstream. Third, domain knowledge and hybrids. We can inject real-world structure into learning by encoding prior knowledge about the domain. For example, geometric priors can guide shape-related factors, Physiological or health-related cues can inform latent associations in biological data. Hybrid architectures, most notably VAE-GAN hybrids, combine probabilistic generation with adversarialism, often yielding sharper outputs and more meaningful latent semantics. In practice, domain guidance helps the model extract transferable, semantically meaningful features, supporting safer, more reliable editing and better generalization. Putting it together, the aim is a clearer map from ideas to visuals or text. With disentanglement, regularization, and domain-informed learning, we can imagine precise edits, lighting while preserving pose, color shifts without resizing, or texture edits that don't misrepresent distance. For researchers, this translates into safer tools, fairer systems, and more trustworthy interpretability, where students and practitioners can articulate why a change happens and anticipate its effect. Beyond the vanilla VAE, there is a family of variants and hybrids that researchers deploy to strengthen latent disentanglement, improve perceptual quality, or speed up training. In this part of the talk, I'll sketch 4 prominent directions you might consider depending on your task and data. First, beta VAE takes a controlled step toward disentanglement by weighting the KL term in the standard VAE objective. By increasing beta above 1, the model is encouraged to use fewer latent factors to explain the data, which often yields more factorized representations. The payoff is interpretable disentangled latents, but the cost is typically a drop in reconstruction fidelity and a tighter limit on capacity. In practice, many teams adopt KL annealing, starting with a small beta and gradually increasing it to let the network learn useful reconstructions before pushing for disentanglement. This trade-off is especially relevant when you want interpretable factors such as pose or lighting in phase data, rather than just any plausible reconstruction. Second, InfoVAE modifies the regularization pressure to preserve information content in the latent codes while still avoiding posterior collapse. Rather than a fixed KL penalty, InfoVAE incorporates a more flexible divergence and an explicit term that maintains mutual information between X and Z. The upshot is a more faithful use of the latent space, sometimes yielding richer representations without sacrificing stability. It's a practical option when you suspect the standard KL constraint is too aggressive for your dataset or architecture. Third, VAE-GAN hybrids pair the generative strengths of VAEs with the sharpness and realism fostered by adversarial training. The encoder-decoder pair remains, but a discriminator guides the reconstructions toward perceptual plausibility. This often produces crisper images with finer textures, which matters when evaluators price realism alongside latent structure. Training stability can be more delicate, so stabilization tricks, feature matching, perceptual losses, and careful balancing of the VAE and GAN objectives are essential. Fourth, there are flow-based and discrete latent alternatives. Flow-based models like Real NVP or GLOW offer a sequence of invertible, easily optimizable transformations with exact likelihoods, facilitating stable training and scalable density estimation. They, however, come with architectural overhead and computational cost. On the discrete side, discretizing the latent space through approaches such as VQVAE can simplify optimization and capture multimodal, discrete factors in the data, often improving compression and downstream interpretability. Up next, 3 threads converge to give you controllable, practical generative models. First, conditional VAEs, where a label or attribute guides both encoding and decoding. Think of a real image turned into a label condition latent, then a new image built from that code and the same label. We'll see how this lets you request a blue car, a smiling face, or a different pose, and how mislabeling can throw things off. Then, beta VAE, which tightens the KL penalty to tease apart independent factors, lighting, color, pose, so changing one factor won't drape the others in confusion. We'll discuss the cost to reconstruction and the value of interpretability. Finally, the VAE-GAN hybrid, merging a structured latent space with a sharpening critic to yield crisp, varied pictures. We'll cover practical gains, training caveats, and how to reason about when to mix these ideas for real projects. Building on the idea that conditioning provides steerable control, we can push CVAEs toward even stronger disentanglement, sharper samples, and broader applicability. I'll walk you through several influential directions: beta VAE, style disentanglement in conditional settings, info VAE, VAE GAN hybrids, and semi-supervised or multi-attribute conditioning. First, beta VAE and structured latent control. In a CVAE, we typically combine the label y with the latent z to generate x. By introducing a beta factor on the KL term, we encourage the approximate posterior Q, z vertical bar, xy, to align more loosely with the prior, promoting factorized, interpretable axes in z that capture independent factors of variation given y. In practice, this means you can separate, say, the shape of an object from its style or lighting, while still honoring the conditioning label. The trade-off is reconstruction quality. Larger beta can lead to blurrier samples if taken too far, so practitioner choice and validation are essential. But when done well, beta VAE or factor VAE inspired penalties can yield latent spaces where traversals in Z correspond to clean, interpretable changes at fixed Y. Second, info VAE as an alternative objective. Rather than relying solely on the standard KL term, info VAE emphasizes preserving information between Z and X under the conditioning Y while still matching to a prior. By adopting a mutual information perspective, often with a combination of KL scaling and distance measures like MMD, we mitigate posterior collapse and retain richer factor information. For CVAEs, this translates into better fidelity to conditioned variations, color, pose, style, without sacrificing the reliability of the conditioning signal. Third, VAE GAN hybrids for realism. A CVAE can be augmented with a discriminator that judges how plausible an image is conditioned on Y. The decoder then receives both Z and Y and is trained with a reconstruction loss plus a GAN loss. The result is samples that closely respect the conditioning while achieving sharper textures and more realistic details than pixel-wise losses alone. Training requires care to balance adversarial and variational terms, but the payoff is evident in many conditional image synthesis tasks. Fourth, disentanglement and semi-supervised conditioning. Techniques like semi-supervised CVAs allow learning from labeled and unlabeled data by jointly inferring Y and Z. You can also exploit multiple attributes, color, pose, lighting by structuring the latent space with separable subvectors or by imposing penalties on total correlation to encourage independence across factors. This makes it possible to manipulate one attribute while holding others constant, even when labels are noisy or partially absurd. In short, advances like beta VAE, disentanglement, info VAE objectives, VAE GAN hybrids, and semi-supervised multi-attribute conditioning extend CVAEs from controllable generation to interpretable, high fidelity, and robust representations. Let's expand our discussion to how beta VAE sits in the broader landscape of disentangled representations and how researchers actually use it in practice. At its core, beta VAE multiplies the KL penalty by a factor beta. Concretely, the objective is still reconstructing the input through Z, but we verbally emphasize the simplification of the latent code. L equals reconstruction term minus beta times D, KLQ, vertical bar X, vertical bar PZ. A larger beta pushes the learned latent distribution closer to the prior and, as a result, tends to factorize the latent space into more independent components. The intuition is simple. When each latent dimension becomes more independent, it's easier to map specific changes in the data to specific latent directions, which improves interpretability. In practice, this means that a beta VAE often yields latent factors corresponding to distinct generative aspects of the data, lighting, pose, color, texture in images, or speaking rate and timbre in audio without forcing each factor to perfectly capture a single ground truth variable. The benefit is twofold. You get representations that are easier to interpret, and you gain intuitive control over generation edit one latent component, and the rest remain comparatively stable. But there is a trade-off. Enforcing stronger independence can reduce the capacity of the model to capture fine-grained details, so reconstruction quality can suffer. If beta is set too high, the model may overlook subtle cues that matter for fidelity. If beta is too low, factors remain entangled and harder to interpret. The design choice setting beta and whether to anneal it during training depends on the task. Interpretability and controllability for creative or scientific analysis, VS. Ultra high fidelity reconstruction. Beyond beta VAE, there are complementary directions that can preserve or even enhance information while promoting disentanglement. Info VAE, for example, modifies the objective to keep the latent code informative about the input while still regularizing the latent distribution. Practically, this means we can encourage a richer, more useful encoding without sacrificing the benefits of latent factorization. In some regimes, Info VAE yields a better balance between reconstruction quality and disentanglement than a vanilla beta VAE. On the generation side, VAE GAN hybrids pair a VAE with adversarial training to improve realism. The VAE encoder provides a structured latent space, while the GAN-like discriminator and adversarial loss push the decoder toward sharper, more lifelike outputs. This can be especially valuable when high-fidelity visuals are essential, but it comes with more delicate training dynamics. Finally, evaluating disentanglement matters. We often use metrics like MIG or other disentanglement scores to quantify how well individual latent axes map to distinct factors of variation. In any case, the aim is clear: achieve usable, interpretable latent factors without sacrificing practical performance. As you design your project, think of beta as a dial for disentanglement versus reconstruction, and consider Info VAE or VAE GAN variants when your priorities shift toward information preservation or realism. Two powerful ideas drive modern generative models, and today I want to move beyond the basics to how we push them further. Variational extensions that encourage structure and disentanglement, and hybrids that fuse the best features of VAEs and GANs. If you already see VAEs as a way to organize latent space and GANs as a way to sharpen samples, these variants give you more control over what the model learns and what it can generate. First, consider beta VAE and related disentanglement-focused variants. The key idea is to adjust the objective to encourage the latent codes to capture independent factors of variation. By setting a beta greater than 1, you amplify the penalty on the KL divergence, which tends to push the posterior toward a factorized prior. The payoff is a more interpretable disentangled latent space where traversals correspond to distinct human interpretable factors such as pose, lighting, or object style. The trade-off is often reconstruction quality. As you push for disentanglement, you may see blur or lost fine detail. This is not a flaw of the framework, but a design choice. If your downstream task rewards factorized control e.g., controllable synthesis, downstream inference, or robust transfer, a beta VAE can be valuable. Extensions also explore adjusting capacity, using free bits or annealing schedules to balance reconstruction against disentanglement while mitigating posterior collapse. Second, Info VAE reframes the objective to preserve information in the latent code more effectively. Rather than simply matching the approximate posterior to the prior, Info VAE incorporates a more flexible information objective that can include mutual information terms or maximum mean discrepancy terms. The practical effect is stronger guidance from the latent code to the generated sample, helping the model make better use of latent variables and maintain diversity without sacrificing stability. In short, Info VAE aims for a more informative latent representation without the harsh penalties that sometimes accompany beta VAE. Turning to VAE GAN hybrids, these architectures blend the two schools explicitly. A VAE supplies a structured latent space and reasonable reconstructions, while a GAN discriminator imposes realism on the outputs. In practice, the VAE's reconstruction path can be augmented or replaced with an adversarial objective, and the latent space can guide the generator to produce diverse yet coherent images. The payoff is sharper, more realistic images and richer variety, with improved stability relative to pure GANs in some settings. Training, however, demands careful balancing. You must align reconstruction objectives, adversarial losses, and any KL or regularization terms. Techniques such as feature matching, perceptual losses, 2 timescale updates, and penalty terms help keep training stable. In real-world research, these tools unlock better realistic synthesis, more effective semi-supervised learning, and robust anomaly detection where the models learn normal patterns or easier to detect deviations. Latent traversals, disentangle factors, and a guided latent space together offer a practical roadmap for interpretable, controllable generation. As always, expect many knobs to tune, but with thoughtful design, the benefits, quality, diversity, and usefulness shine through. This presentation sketches a practical, iterative agenda for continuing inquiry beyond today. The 10 directions are not rigid rules, but flexible paths to test in the coming year. Deeper research into causes, real-world applications, and cross-sector collaboration, ongoing attention to ethics, safety, and inclusivity, broader access through clearer explanations and approachable practice, explicit timelines, measurable checkpoints, and prudent use of affordable open resources. A heightened focus on future-ready skills, curiosity, problem-solving, data literacy, teamwork learned through projects and challenges, and a steady stream of feedback from students, families, and teachers to refine activities. By tying future work to today's lessons, we reinforce the link between current practice and what comes next. With curiosity and persistence, we can plan, test, and adapt toward meaningful change. Recent advances in variational autoencoders are increasingly about going deeper and smarter, not just wider. Let me unpack what that means for researchers who want to push the boundaries beyond the basics you've already seen. First, hierarchical VAEs. These architectures stack latent layers so that the topmost codes capture global abstract structure, the overall scene or object categories, while the lower layers model finer details and textures. In practice, this yields more expressive latent spaces. High-level factors can be swapped or composed without destroying local realism. This also helps when data are complex or multi-scale, such as medical images or long-form scenes, where different levels of abstraction are essential for faithful reconstruction and robust generalization. Second, attention-based designs. Attention mechanisms allow the model to allocate capacity where it matters most, which is crucial when inputs are rich and cluttered. Self-attention, in particular, can capture long-range dependencies and structural relationships that convolution alone might miss. The result is crisper reconstructions and latent representations that better reflect salient regions and dependencies in the data, whether it's a biopsy image, a satellite scene, or a long document. Third, disentanglement and regularization variance. Beta VAE deliberately increases the emphasis on the KL term to promote factorized latent explanations of the data. The payoff is more interpretable factors such as color, pose, or lighting that you can manipulate independently. But the cost is a potential drop in reconstruction fidelity, so researchers tune beta to balance interpretability with quality. InfoVAE takes a related route by preserving mutual information between latent codes and inputs, mitigating posterior collapse and preserving useful structure in the latent space. For sample quality, VAE GAN hybrids blend the probabilistic reconstruction with an adversarial objective, producing sharper, more realistic images. Fourth, integrating with reinforcement learning and causal reasoning. In world modeling settings, VAEs learn latent representations of observations, while the model learns dynamics in that latent space to plan actions or roll out imagined futures. This latent planning can improve sample efficiency and decision quality in dynamic environments. Causal inference adds another layer. Disentangling what happened from why it happened enables experiments and interventions to be more informative and robust, especially in real-world deployments where data are noisy and interventions are costly. Finally, applications and direction. Privacy-preserving healthcare analytics, fraud and anomaly detection in finance, and coherent text or dialogue generation in NLP are all increasingly tackled with these richer VAEs. The field also seeks faster training, clearer evaluation protocols, and standard benchmarks to compare models fairly. In short, the trend is toward architectures that learn deeper, more controllable representations, coupled with principled regularization and cross-domain integration. Building on the core VAE picture, there are several influential extensions that let us tune what the latent code represents and how sharp the generated samples can be. I'll sketch 4 directions you'll often see in the literature. Beta VAE for disentanglement, Info VAE for information efficient regularization, VAE GAN hybrids for realism, and explicit efforts to structure latent space for interpretable factors. First, beta by ACE. The central idea is to introduce a hyperparameter beta that scales the KL regularizer. When beta is raised above 1, the model is pressured to learn a more compact, factorized latent representation. In practice, this often yields latent axes that align with distinct generative factors, things like stroke thickness, slant, or digit width in handwritten digits. The upside is improved interpretability and controllability. You can mix and edit specific factors by perturbing corresponding latent dimensions. The caveat is that too large a beta can degrade reconstruction quality or even cause underfitting. The common remedy is a warm-up schedule for beta, gradually increasing it during training, and to ensure the model has enough capacity to capture the data distribution. Second, InfoVAE. This family reframes the regularization to manage the information content that Z can carry about X. By tuning how much information passes through the bottleneck and how tightly the aggregated posterior must resemble the prior, InfoVAE provides a flexible trade-off between reconstruction fidelity and latent descriptiveness. It helps mitigate issues like posterior collapse while still encouraging useful, task-relevant representations. In short, InfoVAE gives you an explicit dial for preserving meaningful structure in Z without sacrificing the stabilizing prior regularization. Third, VAE-GAN hybrids. These approaches pair the probabilistic encoder-decoder with adversarial training to enhance sample realism. Instead of relying solely on the reconstruction error, a discriminator guides the decoder to produce outputs that are indistinguishable from real data. The net effect is sharper, more photorealistic or texture-rich samples, addressing the blurriness sometimes seen in plain VAEs. These hybrids can be extended with perceptual losses or multi-scale discriminators to balance fidelity with faithful latent modeling. Fourth, disentanglement and structured priors. Beyond beta VAE, methods like beta TCVAE penalize the total correlation among latent dimensions to encourage true statistical independence. This improves factorization of latent factors and often translates to more controllable generative behavior. Researchers evaluate disentanglement with metrics such as mutual information gaps and related probes, and increasingly consider semi-supervised variance when some labels are available to guide factor discovery. Here are ideas to guide your reading and hands-on practice as you deepen your understanding of VAEs and their variants. We'll begin with curated resources for deep dives, then move to practical experiments that sharpen intuition and technical skill. First, study the foundational papers by Kingma and Welling with care. They anchor the whole framework and the reparameterization trick that makes learning feasible. Next, engage with accessible tutorials that unpack reparameterization for beginners and gradually introduce nuance, how stochasticity is injected, how priors shape the latent space, and how optimization behaves under stochastic gradients. Then, explore recent surveys and synthesis papers that chart advances in VAE architecture, objective design, and training stability. This sets you up for informed experimentation rather than ad hoc tinkering. Now for hands-on exploration that goes beyond the basics. Implement VAEs with varied architectures, different encoder divided by decoder depths, skip connections, or conditional inputs to observe how capacity and inductive biases influence reconstruction, quality, and latent organization. Experiment with alternative reparameterization techniques and objective terms in practice. Extend datasets beyond toy examples to open source benchmarks such as MNIST, CIFA, 10, Syllabe, or 3D-shaped datasets to test generalization and optimization across domains. The aim is to connect theory with reproducible results you can cite and build on. As you gain confidence, branch into advanced VAE variants and hybrids. Try beta VAE, which increases the weight on the KL term to encourage disentangled latent factors. Assess how changing beta affects disentanglement versus reconstruction fidelity. Explore InfoVAE or related information maximizing formulations that incorporate mutual information terms to preserve useful structure in the latent space. Experiment with VAE-GAN hybrids that couple an adversarial discriminator to sharpen sample quality while maintaining a probabilistic latent representation. When you tackle latent disentanglement explicitly, use metrics like mutual information gaps, the total correlation objective, or downstream task robustness to quantify progress. These explorations help move from what works to why it works and enable principled comparisons across datasets. Finally, sustain a cycle of curiosity, documentation, and dialogue. Take short notes, sketch simple diagrams, and run small ablations to understand causal effects. Discuss results with peers or mentors to gain new perspectives. Pace your experiments and maintain a lightweight log of what works and what doesn't. If you are unsure where to start, pick one architecture and build a compact project, an encoder-decoder with a hidden layer, for example, and observe how latent variables organize information versus plain propagation. Remember to cite sources and read with a critical eye. With steady practice and a curious mindset, you will contribute ideas that advance practical generative modeling in your own projects. This variational autoencoder notebook explores one of the most important models in generative AI. Unlike standard autoencoders that only compress and reconstruct data, VAEs add a layer of probability. This lets them capture uncertainty and variation and makes the model capable of creating new data that looks realistic and diverse. The key idea is simple: encode complex data into a smaller, smooth space then decode it back into something meaningful. What makes VAEs powerful is that this space is continuous, which means you can move through it and generate endless new variations, images, sounds, or other kinds of data. This notebook shows how the model learns to balance two goals: rebuilding data accurately and keeping the latent space smooth and well structured. Together, these goals make sure the outputs are not only close to the originals but also flexible and creative. VAEs are more than a technical exercise, they are a foundation for many creative and scientific applications. They can help artists explore new forms, support scientists by generating synthetic data, or act as a starting point for more advanced generative models. By working through this notebook, you'll see how probability and optimization come together to give machines a deeper understanding of data. It's a step towards systems that don't just memorize but learn the patterns of the world and use that knowledge to create. In this section, we set up the necessary dependencies for our project. We begin by importing some basic utility modules from Python standard library, such as mapping, union, and optional, from the typing module, which help us specify flexible data types later in our code. The path class from the pathlib module is imported to handle file system paths in a more intuitive way. Next, we bring in numerical computing tools with NumPy, which is fundamental for data manipulation and mathematical operations. The argparse module is included to facilitate command line argument parsing, enabling flexible script configurations. Since our focus is on deep learning, we import core components from PyTorch, including the main torch package along with its neural network module torch, NN, functional API iTorch, NN, functional, and the optimizer package torch, Optim. These will allow us to define, train, and optimize neural networks. For visualization, we bring in plotless graph objects and express modules, which offer powerful tools for creating interactive plots, as well as matplotlib's pyplot for static visualizations. The Torch Vision package is also imported, providing datasets, models, and transformation utilities essential for handling image data. We include the OS module for operating system interactions, Pickle for data serialization, and TQDM notebook for progress bars that give us visual feedback during lengthy computations. Finally, we import future features to ensure compatibility across different Python versions, specifically the print, function, and division features to enhance code consistency and readability. Altogether, these imports establish a comprehensive environment for developing, training, and visualizing variational autoencoders within this notebook. This section is focused on setting up reproducibility for the code. It begins by importing the random module, which is used for generating random numbers in Python. To ensure that the results are consistent across different runs, we set a seed for Python's built-in random module to 0. Moving on, we set the seed for PyTorch's random number generator to 42, which helps in making the deep learning experiments reproducible. Similarly, the NumPy library's random seed is also set to 42, ensuring that any random operations performed with NumPy produce the same results each time. Since this notebook might utilize GPU acceleration, we also set the seed for CUDA's random number generator to 0. Additionally, to make computations deterministic on the GPU, we configure PyTorch's backend by setting the QDNN backend to deterministic mode. This is achieved by enabling the deterministic flag, which can impact performance but guarantees reproducibility. Finally, we disable CUDNN's benchmarking feature, which can introduce variability in the computations, ensuring consistent results across different runs. This setup is crucial in experiments where reproducibility is of utmost importance, especially when training deep learning models. This code snippet begins by creating a simple dataset consisting of 10 random values generated using PyTorch's random number generator. These values are stored in a tensor called .data. Next, the code defines two linear transformation layers, both with an input and output feature size of 10, named deterministic transform 1 and deterministic transform 2. These layers are meant to serve as deterministic transformations, likely to be applied sequentially or in some combination within a neural network model. Finally, the code specifies an expected output tensor called .gold output, which is a tensor of 10 ones. This gold output serves as a reference or target, probably for comparison purposes during training or evaluation. Overall, this setup provides a minimal example of data preparation, model component definition, and expected results in a PyTorch-based deep learning workflow. This code snippet begins by making a stochastic prediction. It first applies a deterministic transformation, let's call it deterministic transform 1, to the input data to compute the mean of the predicted distribution. For the standard deviation, it simply creates a tensor filled with ones that matches the shape of the data, implying a fixed unit standard deviation. Next, it samples from a normal distribution characterized by the calculated mean and this standard deviation. These random samples introduce stochasticity into the prediction process, which is essential for models like variational autoencoders. Once the sampling is done, the code applies another deterministic transformation, deterministic transform 2, to this sampled data to produce the final predicted output. The loss is then computed using the mean squared error between this predicted output and the ground truth, or gold output. After calculating the loss, the gradients are reset to 0 for the first deterministic transform, ensuring that gradients are not accumulated across iterations. The backward pass is then performed on the loss to compute gradients, setting the stage for optimization. Finally, although not shown explicitly here, the next step would be to update the model parameters using an optimizer, such as ADAM or SGD, to minimize this loss and improve the model's predictions. This code snippet begins by generating a stochastic prediction based on some deterministic transformations. First, it applies a transformation labeled as deterministic transform 1 to the input data to produce a mean prediction, which we store in predmean. For the standard deviation, it simply creates a tensor of ones with the same shape as the data, indicating a fixed unit variance across all predictions. Next, it draws 10 random samples from a standard normal distribution stored in background source. These random samples are then scaled by the predicted standard deviation and shifted by the predicted mean, effectively resampling from the predicted distribution to generate diverse possible outcomes. This process results in a set of samples called sampling. The sample data then passes through another deterministic transformation, the deterministic transform 2, to produce the final output predictions, which we store as .pred output. To evaluate the quality of these predictions, the code computes the mean squared error loss between the predicted output and the true target values, gold output, using F, MSE, loss. Before backpropagation, it clears any existing gradients on the first transformation to prevent accumulation, then performs backpropagation on the loss to compute gradients. The final comment indicates that the next step would be to update the model parameters through some optimizer, which is a typical step in training neural networks. This approach allows for stochastic sampling within the model, enabling it to learn probabilistic representations. In this segment of the code, we start by generating a tensor of random data with 10 elements using torch runtime. Next, this data is passed through a transformation function, deterministic transform 1, which produces a mean prediction, pred mean. To define the uncertainty around this prediction, we set pred std as a tensor of ones with the same shape as the data, representing a standard deviation of 1 for each element. With these parameters, we create a normal distribution object specifying the predicted mean and standard deviation. Using the rsample method, we draw a sample from this distribution. The use of rsample is crucial because it allows us to perform differentiable sampling, implementing the reparameterization trick essential in variational autoencoders. This sample data, which incorporates some stochasticity, is then passed through a second deterministic transformation, deterministic transform 2, to produce the final output, pred output. We then compute the mean squared error loss between this predicted output and the target, gold output. Before backpropagation, we reset the gradients of deterministic transform 1 to 0 to prevent accumulation. We call loss. Backward to compute the gradients, which will propagate back through the network, including through the reparameterization step. Finally, we extract the gradient of the weights in deterministic transform 1, which can be used for optimization or analysis. This process exemplifies how stochastic sampling and differentiability are combined in variational autoencoders to enable training via gradient-based methods. This section of the code sets up some key hyperparameters for training a variational autoencoder. It begins by defining the dimensionality of the latent space, setting it to 2 dimensions, which is a common choice for visualization purposes and aligns with the original VAE paper's parameter count, although that paper used roughly 3 times as many parameters. Next, it specifies the number of training epochs as 40, indicating how many times the entire dataset will be passed through the model during training. The batch size is set to 128, meaning that during training, the model will process 128 samples at a time before updating its weights. The capacity parameter is set to 64, which likely controls some aspect of the model's bottleneck or regularization, although its specific role depends on further context. The learning rate is defined as 0. 001, a common starting point that balances convergence speed and stability. The variational beta parameter is set to 1. This parameter is used in the beta VAE framework to control the trade-off between the reconstruction loss and the regularization term, encouraging disentangled representations when increased. The use GPU flag is set to true, indicating that GPU acceleration is preferred if available. Finally, the code determines the device to run the computations on. If GPU usage is enabled and a CUDA-compatible GPU is available, it assigns the device accordingly. Otherwise, it defaults to the CPU. This setup ensures efficient training by leveraging hardware acceleration when possible. This code section begins by importing the necessary modules for data handling and transformation. It uses torch vision transforms to define a sequence of image transformations, in this case, converting images into tensor format suitable for neural network input. Next, it leverages the data loader class from Torch utils data to facilitate batch processing and shuffling of data during training and testing phases. The code then proceeds to load the MNIST dataset, which consists of handwritten digit images. For the training set, it specifies the root directory, enables downloading if the data isn't already present, and applies the transformation defined earlier. The same process is repeated for the test set, with the distinction that the test data loader's batch size is set to either 10,000 or the specified batch size, whichever is larger, ensuring that the entire test set can be processed in one go if desired. Overall, this setup prepares the MNIST data for efficient training and evaluation of a deep learning model with proper transformations and data loading pipelines in place. This section defines an encoder class, which is a fundamental part of a variational autoencoder. The encoder is a neural network module that takes in an image, in this case a single channel image, and produces two key outputs, the mean and the log of the variance of the latent space distribution. The design starts with two convolutional layers. The first convolutional layer takes the input image and applies filters to extract features, reducing the spatial dimensions from 28 by 28 pixels to 14 by 14 pixels, thanks to the stride of 2 and padding. The second convolutional layer further processes these features, doubling the number of channels and reducing the spatial size again to 7 by 7 pixels. After these convolutional layers, the feature maps are flattened and fed into two fully connected layers. One of these produces the mean vector and the other produces the log variance vector, both of which have a size equal to the dimensionality of the latent space specified by .latent dim. The choice to predict the log of the variance instead of the variance itself is a stability measure, which helps prevent numerical issues during training. Additionally, an activation function, ReLU, is used after the convolutions to introduce nonlinearity, enabling the network to learn more complex representations. This encoder effectively compresses the input image into a probabilistic latent representation, which is central to the variational autoencoder framework. This code defines a class called Variational Autoencoder, which inherits from the base neural network module. Inside the constructor, it initializes two key components, an encoder and a decoder, each configured with specified hidden channels and a latent dimension. The encoder compresses the input into a latent representation, producing parameters for the mean and log variance, while the decoder reconstructs the input from this latent space. The forward method takes an input tensor, passes it through the encoder to obtain the mean and log variance of the latent distribution, and then samples a latent vector using the reparameterization trick implemented in the latent sample method. This trick allows the model to perform stochastic sampling while enabling gradient-based optimization. The sample latent vector is then fed into the decoder to produce a reconstructed version of the original input. The method returns the reconstructed output along with the mean and log variance of the latent distribution. The latent sample function handles the sampling process. During training, it computes the standard deviation from the log variance, then samples from a normal distribution with the specified mean and standard deviation using the R-sample method, which supports backpropagation. During evaluation or inference, it simply returns the mean, avoiding stochasticity. Finally, an instance of this variational autoencoder is created with specified capacity and latent dimensions and moved to the appropriate device, such as a GPU if available. The total number of trainable parameters in the model is then computed by summing the number of elements across all parameters that require gradients. This code defines a function called .VE_loss, which calculates the loss for a variational autoencoder. It takes 4 inputs: the reconstructed output, recon, x, the original input, x, the mean, mu, and the logarithm of the variance, Ca log var, from the encoder's output. First, it computes the reconstruction loss using binary cross entropy, which measures how well the reconstructed image matches the original. To do this, both recon x and x are flattened into vectors of size 784, corresponding to the pixels of a 28 by 28 image, and the loss is summed over all elements. Next, the function calculates the Kullback-Leibler divergence, or KL divergence, which measures how much the learned latent distribution deviates from the prior distribution, typically a standard normal distribution. This term is derived from the variational principle and involves the mean, mu, and the log variance, log var. The formula uses the sum over all dimensions, incorporating the properties of the Gaussian distribution. Finally, the total loss combines the reconstruction loss with the scaled KL divergence, where variational beta is a hyperparameter that adjusts the importance of the KL term in training. This combined loss guides the autoencoder to produce accurate reconstructions while keeping the latent space well structured and close to the prior distribution. This section begins by importing some essential libraries for data handling and numerical computation, specifically pandas and numpy. These are fundamental for managing datasets and performing array-based operations throughout the notebook. Next, the code defines a utility function called makeAverager. This function is designed to create and return a nested function called averager, which maintains a running average of a sequence of numbers. When you call makeAverager, it initializes 2 local variables, count and total, both starting at 0. These variables keep track of how many values have been added and the cumulative sum of those values, respectively. The inner function averager takes an optional new value. If a new number is provided, it updates the total sum and count, then calculates and returns the current average. If called with none, it simply returns the current average without modifying the state. This setup allows you to continuously update the running average as new data points come in, or retrieve the current average at any time without adding new data. Overall, this utility is a lightweight way to efficiently compute and keep track of averages during training or evaluation phases, where real-time statistics are often necessary. This section begins by initializing a variational autoencoder, specifying the number of hidden channels using the variable tot capacity, and setting the dimensionality of the latent space with latent DIMs. The model is then moved to the appropriate device, whether that's a CPU or GPU, to ensure efficient computation. An Adam optimizer is set up with the model's parameters, a learning rate defined by n learning rate, and a small weight decay for regularization. Next, the model is switched to training mode, which activates certain layers like dropout or batch normalization that behave differently during training versus inference. An empty data frame is created to keep track of logging information, and a single batch of test data is fetched to evaluate the model's initial performance on unseen data, which is logged using a function called .run on test batch. An empty list is initialized to store the average training loss per epoch. The training process then begins, with the progress bar showing the current epoch and a placeholder for the loss. Inside the epoch loop, an averager object is created to compute the mean loss over the epoch. Within each epoch, another progress bar iterates over the training data loader, which supplies batches of images. For each batch, the images are moved to the device to match the model's location. The autoencoder processes the batch, producing a reconstructed image, as well as the mean and log variance of the latent distribution, which are essential for the variational aspect of the autoencoder. The next step, which is not fully shown here, would involve calculating the reconstruction error, how close the reconstructed images are to the original inputs, and combining this with the KL divergence term that encourages the latent space to follow a prior distribution. This combined loss guides the training of the model, helping it learn meaningful representations of the data. This section begins by importing the Plotly Express library, which is used for creating interactive visualizations. It then sets a parameter called n samples, which determines how many data points will be visualized, with the default value of 1470, and this can be adjusted using a slider. Additionally, there is a Boolean parameter named 9p size, exactly as std, that controls whether the size of the markers in the plot should be scaled precisely according to their standard deviation or not. Next, a function called plot latent params is defined. This function takes in a data frame containing the latent space parameters and a flag indicating whether to set the marker size exactly as the standard deviation. Inside the function, if mo size exactly as std is true, the maximum marker size is set to 200. Otherwise, it remains unspecified, allowing Plotly to scale sizes automatically. The core of the function creates an interactive scatter plot. It filters the data frame to include only the first n samples data points. The plot maps the latent space coordinates mu x and mu y to the x and y axis respectively. It also animates the points over different epochs, which allows us to see how the latent representations evolve during training. Each point in the plot is grouped by the image END identifier to maintain consistency across frames. The size of each marker corresponds to the std x value, representing uncertainty in the latent encoding, and the color indicates the class label of each data point is less than #0. Phi hash is greater than additional parameters set the color palette, plot dimensions, size limits, and the range of axes to focus on the region from -5 to 5 inches both directions. Finally, the function is called with the data frame named df log, and the size scaling is controlled by the size exactly as std parameter. This creates an interactive, animated visualization of the latent space, allowing us to explore how the model's learned representations change over training epochs, with marker sizes reflecting the uncertainty of each encoding. This code begins by importing the Plotly Express library, which is used for creating interactive visualizations. Next, it sets a variable called .n samples to 190, which determines the number of samples to generate or analyze. The variable a, size exactly as std, is a boolean that, when set to false, indicates that the size of the visualization elements won't be strictly tied to the standard deviation, providing flexibility in how the plots are rendered. The core of this section involves creating an untrained variational autoencoder, or VAE. This is done by instantiating a variational autoencoder object, specifying parameters such as hidden channels, which is set to a variable called capacity, and latent dim, which determines the size of the latent space. The model is then moved to the appropriate device, whether it's a CPU or GPU, to prepare for computation. Following this, an empty data frame called df log3 is initialized. This data frame will be used to log or store the results of the model's processing. The run on test batch function is then called, passing in this data frame the untrained VAE, an index, and the test data batches, test batch X and test batch Y. This function likely runs the VAE on a batch of test data and logs relevant parameters or results into the data frame. Finally, the plot latent params function is invoked, which takes the log data and visualizes the latent space parameters. The max size parameter is set based on the size exactly as std flag, controlling the visual representation, perhaps in terms of marker sizes or plot scales. Overall, this segment sets up and visualizes an untrained VAE's latent space, providing a baseline understanding before training begins. This segment of code is enclosed within an if statement that is set to false, meaning it won't execute during normal runs. The purpose of this block is to handle the downloading and loading of a pre-trained variational autoencoder model. It begins by defining the file name for the pre-trained model, in this case, way2d, pthtrim. Next, it checks if a directory named pre-trained exists. If not, it creates this directory to store the downloaded file. The code then prints a message indicating that a download is about to start. It constructs the full file path by combining the pre-trained directory with the file name. Using the URL library, it retrieves the pre-trained model from a specified URL and saves it to the designated file path. After the download, the code loads the saved model, waits into the VAE instance using load state dict. It then moves the model to the appropriate device, whether CPU or GPU, to prepare it for inference or further training. Finally, it prints a confirmation message indicating that the model has been successfully loaded onto the specified device. Since this block is wrapped in an if-false condition, it acts as a template or optional step, which can be activated if needed. In this section, the model is switched to evaluation mode by calling .ve eval, which ensures that certain layers like dropout and batch normalization behave appropriately during inference. An averager object is created to keep track of the test loss across batches. Using a torch, no, grad, context, we disable gradient calculations to improve efficiency during testing. We then initialize a progress bar with TQDM, which displays the current batch progress and the loss, giving us real-time feedback on the evaluation process. Within the loop, each batch of images from the test data loader is moved to the appropriate device, such as a GPU. The VAE model processes each batch, producing a reconstructed image along with latent space parameters, the mean, latent, mu, and log variance, latent, log var. The reconstruction loss is computed using these outputs, which measures how well the autoencoder is performing. The progress bar is then updated with the current batch's loss, averaged over all previous batches, providing a live view of the model's performance. After processing all test batches, the code prints out the overall average test loss. Following this, a dictionary called label2img is built using a default dict of lists. This dictionary is meant to store images organized by their labels for easy access later. The code iterates over the test data loader again, moving each batch of images to the device. For each image in the batch, the code maintains the singleton batch dimension and prepares to associate images with their labels, although the specific assignment part is not shown in the snippet. This setup facilitates tasks like visualizing images by class or performing label-specific analysis in subsequent steps. This code begins by defining a function called reconstruct images, which takes a batch of images and a model as inputs. The function sets the model to evaluation mode to disable any training-specific behaviors, and then, within a no-gradient context to save memory and computation, it passes the images through the model. The output images are then clamped between 0 and 1 to ensure pixel values stay within valid bounds, and these reconstructed images are returned. Next, the code selects a specific digit, in this case 5, and a style variation index, which allows us to pick particular images from a dataset. Using these indices, it retrieves an image from a predefined label to image mapping. It then concatenates this original image with its reconstructed version obtained by passing it through the Variational autoencoder, or VAE, and moves the result to the CPU for visualization. The code then proceeds to encode the original image using the VAE's encoder, which outputs the mean and log variance of the latent distribution. To obtain the standard deviation, it divides the log variance by 2 and exponentiates the result, squeezing unnecessary dimensions for clarity. The means, representing the latent space encodings, are also squeezed and moved to the CPU. A figure is set up with a tall aspect ratio to display the images. It uses a utility to create a grid of images, showing both the original and reconstructed images side by side, with the grid permuted to match the correct color channel order. The plot is titled Source, Reconstructed, and Access are turned off for a cleaner look. Finally, the code sets a large number of samples, 5000, for potential sampling from the latent space. It constructs a multivariate normal distribution using the means and standard deviations derived from the encoder. This distribution models the latent space of the VAE conditioned on the input image, enabling further sampling or analysis in the latent domain. In this segment of the notebook, we start by importing the necessary utility functions from TorchVision, specifically for visualizing images. Next, we retrieve a batch of images and labels from the test data loader by calling nexiter test data loader. Using these images, we generate the reconstructed versions by passing them through the trained variational autoencoder or VAE and then moving the reconstructed images to the CPU for visualization purposes. To visualize the original images, we set up a large figure with dimensions of 17 by 17 inches. We then use torch vision utils, make, grid to arrange a subset of the images, specifically images 1 through 50 into a grid with 10 images per row and a padding of 5 pixels between images. The grid tensor is permuted to match the height, width, and color channel order expected by matplotlib and then displayed with the title indicating these are some original images. The axes are turned off for a cleaner look. Following that, we perform a similar visualization for the reconstructed images generated by the VAE. We set up another large figure, create a grid of the reconstructed images in the same manner, and display them with a title indicating these are VAE reconstructions. Again, axes are turned off to emphasize the images. Additionally, there are commented out sections showing how one could visualize these images using Plotly instead of Matplotlib. This alternative approach would produce interactive visualizations with options like color scales and titles, providing a different way to explore the original and reconstructed images. This function, named interpolation, takes in a parameter called lambda1 along with the trained model and two images, img1 and img2. It begins by disabling gradient calculations to improve efficiency, since the operation is purely inference. Next, it moves the first image to the appropriate device, such as a GPU if available, and passes it through the model's encoder to obtain its latent representation, which we call latent 1. The same process is repeated for the second image, resulting in latent 2. The core idea here is to generate an intermediate image by interpolating between these two latent vectors. This is achieved by taking a weighted sum of the two latent vectors, where lambda1 controls the interpolation factor. If lambda1 is 0, the output will be identical to the first image, and if it's 1, it will be identical to the second. Values in between create a smooth transition. Finally, the interpolated latent vector is passed through the model's decoder to reconstruct an image. The output image is then clamped to ensure pixel values are within the valid range of 0 to 1, moved back to the CPU and returned. This process allows us to generate a seamless transition between two images by manipulating their latent representations. In this section, we start by setting our variational autoencoder model into evaluation mode, which ensures that any layers like dropout or batch normalization behave appropriately for inference. We then define the number of interpolations we want to generate between two images, choosing 40 for a smooth transition. Next, we select the starting and ending digits for our interpolation. These are controlled via sliders, allowing us to pick any digits from 0 to 9. Additionally, we specify a style index which corresponds to different variations or styles of the digit images. Using these parameters, we retrieve the corresponding images from a preloaded collection which organizes images based on digit label and style. These images will serve as the start and end points of our interpolation. To generate the transition, we create a range of lambda values between 0 and 1, evenly spaced according to our specified number of interpolations. For each value in this range, we perform an interpolation in the latent space of the VAE, gradually morphing the start image into the end image. These interpolated images are then concatenated into a larger tensor to visualize the entire transition smoothly. Finally, we visualize the sequence using matplotlib. We arrange the images into a grid, making it easy to observe the gradual transformation from the initial digit to the final one. The plot is titled to indicate that this is a VAE-based interpolation, moving from the top left to the bottom right of the grid, and axes are turned off for a cleaner look. This setup provides a clear visual demonstration of how the VAE smoothly transitions between different digit images in its learned latent space. In this segment of the code, we set the variational autoencoder model to evaluation mode, ensuring that layers like dropout or batch normalization behave appropriately for inference. We then enter a no gradient context with torch, no, gray, which disables gradient calculations to speed up the process and reduce memory usage during inference. Within this context, we generate a batch of latent vectors by sampling from a standard normal distribution. Specifically, we create 128 vectors, each of dimensionality, latent, DIMS, and place them on the appropriate device, whether CPU or GPU. These latent vectors serve as the prior distribution from which we sample, reflecting our assumption that the latent space follows a Gaussian distribution. Next, we pass these latent vectors through the decoder part of the variational autoencoder to generate corresponding images. The output images are brought back to the CPU and clamped between 0 and 1 to ensure proper pixel value ranges for visualization. To visualize the generated images, we use matplotlib's imshow function, creating a grid layout that displays 100 images arranged in a 10 by 10 grid with some spacing. The images are displayed without axes for a cleaner look, and the overall figure is titled to indicate that these images are generated from the prior distribution of the VAE. There is also a commented out section that shows how one could alternatively visualize these images using Plotly, which offers interactive features and a different aesthetic style. However, for static images, Matplotlib provides a faster and straightforward visualization method. This process demonstrates how the VAE can generate diverse samples solely from the latent space, showcasing its generative capabilities. This piece of code sets up a fun visualization to explore how a trained variational autoencoder behaves in its 2D latent space. It begins by importing the necessary plotting library, matplotlib, to display images. Then, it defines a variable called latence limbs, which determines the range for the latent space sampling, and a parameter num interpolations specifying how many points will be generated along each axis for the grid. Next, there's a check to ensure that the model was trained with exactly 2 latent dimensions, since this visualization relies on a 2D latent space. If the number of latent dimensions is in 2, it prompts the user to adjust the parameters accordingly. Within a no-gradient context, to save computation, the code creates a grid of points in the 2D latent space. It does this by linearly spacing points along both axes within the specified limits, then stacking these to form a grid of coordinate pairs. This grid effectively covers a square region of the latent space. Once the grid of latent vectors is ready, these vectors are passed through the decoder part of the autoencoder to generate corresponding images. The generated images are moved back to the CPU for visualization purposes. Finally, the code uses matplotlib to display all these reconstructed images in a single grid, which allows us to see how the autoencoder's output varies smoothly across the latent space. This visualization provides insight into how the model encodes different features and transitions between different generated samples. This section begins by importing the necessary library for plotting, which is matplotlib pyplot. Next, it introduces a parameter called num interpolations, which is set to 50 by default, and it determines how many points will be sampled along each axis in the 2D latent space for interpolation. The code then imports the normal distribution functions from SciPy, stats, which will be used to map between the probability space and the latent space via the inverse cumulative distribution function, or ICDF. A normal distribution object is created with a mean of 0 and a standard deviation of 1, representing a standard normal distribution. Within a no-gradient context to optimize performance, the code constructs a grid of points in the latent space. It does so by creating linearly spaced values between 0, 0, 0, 1 and 0, 999 to avoid boundary issues for both axes. These are then combined to form a grid of coordinate pairs which are reshaped into a two-dimensional tensor representing each point in the grid. Next, the code applies the inverse CDF of the normal distribution to these grid points, transforming uniformly spaced values into values that follow the standard normal distribution. This effectively maps the grid from a probability space into the latent space of the variational autoencoder. The resulting latent vectors are moved to the appropriate device, such as a GPU if available, and passed through the decoder part of the VAE to generate corresponding images. These images are then moved back to the CPU for visualization. Finally, the code sets up a large figure using matplotlib and creates a grid of the reconstructed images, which visually represent the interpolation across the latent space. This allows us to observe how the VAE smoothly transitions between different points in the latent space, generating a continuous variation in the output images. In this notebook, we built and trained a variational autoencoder and saw how it learns to compress complex data into a smaller, meaningful space called the latent space. From there, Random points in that space can be decoded back into new, realistic data. This shows how machines can go beyond memorizing examples and instead generate fresh, varied outputs that still reflect the original patterns. One of the most striking parts of VAEs is how they can smoothly move or interpolate between different data points. This reveals hidden relationships within the data and shows how the model understands structure at a deeper level. It also points to many practical uses like generating new images, expanding datasets, or supporting other unsupervised learning tasks. We've also seen how VAEs balance two key goals: accurately reconstructing data and keeping the latent space organized and regular. This balance is what makes them so effective at producing diverse yet meaningful results. As you move forward, I have already shared the code for this notebook in Teams. Please execute it on your end and let me know if you run into any issues. I'll be happy to guide you through.